is there a follow-up? Is there another Kepler beyond this Kepler? You're mapping one segment of the sky. Mm-hmm. Is the goal to just keep doing more and getting more and more pieces?
Kepler is a step, and that was mentioned earlier. First we found planets, ground-based planets. Now we're in space, we're finding planets as small as the Earth. We'll learn whether they're frequent or not. Now, if they are frequent, then the next step, the next mission, will look at that, blank out the star, look at the spectra of the planet, and tell you about its atmosphere. If they're very rare, then the mission that will follow us is a much bigger mission. The first mission is very expensive. The second mission, which requires many telescopes to look very far out to find enough transits, enough planets, is extremely expensive. So the National Academy of Sciences has told us, find out how many they are and which kinds of stars they're around, and then we will build a mission to follow yours to find out about their atmospheres.
Okay. We're going to go on to the LCROSS mission, and Tony, you've been the principal driving force behind that. Now we have a short video of that mission. This is an animation, and there's no soundtrack, so I'm going to ask you to provide a running commentary, and then we're going to come back and discuss it further.
Okay.
So can we go ahead and roll that tape?
So the LCROSS mission took advantage of a spent upper stage of the Centaur rocket that propelled us to the moon. And in this part of the graphic, the green line is the trajectory of the LCROSS mission. You see it flew by the moon and then went into a large elliptical orbit around the Earth. And finally, it catches up to the moon after about 4 months and impacts the moon. Here you see the two components of the LCROSS spacecraft, the spent upper stage, which is the large white cylinder, and then the shepherding spacecraft, which was the paneled, smaller spacecraft at the back. What we're doing here, this shows the final portion of our mission. 9 hours before we impact the moon, we separate from that spent Centaur. The shepherding spacecraft spins around to get its sensors. You'll see it do a braking burn. We wanted to observe the impact close, but not that close. So we do a little braking burn to put a little distance between us and the impacting Centaur, and we trail it all the way into the moon. We did the separation. We were about 9 hours out from the moon. The separation we achieved was 4 minutes, so we were trailing 4 minutes behind. We targeted a permanent shadowed region at the south pole of the moon. After impact, the shepherding spacecraft flies at the impact site, gathering data real time, flying eventually through the debris cloud itself and impacting itself on the moon about 4 minutes afterwards. And that's what this artist rendition shows here. And you can see the conceptual ejecta plume coming up out of the dark crater as we head on in and impact ourselves. And this is as it may have looked from the surface if you were observing it, if you were so lucky to be standing on the moon while it happened.
Okay, so that was our video of the LCROSS project, and I take it that that video was produced before the mission itself, but the mission itself has taken place already, I believe, in 2009.
Yeah, it impacted last October.
And what did it find? It was looking for water. Did it find it?
Yes, we did find water, and more importantly, we found a particular flavor of water we were very interested in, and that's water ice. Leading up to the LCROSS impact, there were some other observations by other missions orbiting the moon and some that just flew by the moon that sensed water bound in the minerals of the moon.
Which would make it hard to extract?
Very hard to extract and at very small concentrations. It'd take a football field area of lunar dirt to make about a small cup of water. Here, what we found was gallons, hundreds of gallons of water concentrated in one area. So the concentrations were much greater, and they're water ice, which really indicates an origin for the water. It helps us understand actually the processes that have been affecting the moon.
When you say you detected a certain amount of water, you mean that's how much was kicked up by the impact, not how much remains?
No, so we made a very small little impact onto a much larger crater. The crater we impacted, Cabeus, is about 100 kilometers across. And the shadowed region that has temperatures that are exceedingly cold, minus 240 degrees below 0 centigrade, was many hundreds of kilometers across an area. Our crater we made was about 30 meters across, about the size of a tennis court. And the ejecta that flew out of that, the debris that flew out of it was, we saw approximately more than 4% water content in the debris that flew out of that. That translates to several hundred kilograms worth of water.
Now, we have some still pictures of the LCROSS mission also. We're going to show those pictures and discuss them. So can we see the first slide, please? Okay, so there it is.
So this is the instrument suite for the LCROSS payload. So what was very unique about the LCROSS mission was the unique vantage point we had from the shepherding spacecraft. As we flew directly down at the moon, we used these 9 instruments that were all integrated and built at NASA Ames with commercial industries from across the United States to make the measurements that I've just described. They include 5 cameras, spectrometers, and radiometers that basically separate the light and look for the various components that could make up the materials.
And that was able to send all the information back to Earth before it itself crashed?
It was all what we call bent pipe, real time. We had about a megabit per second relay to Earth, and so it took data, immediately transmitted it to Earth because you had no storm forward on this mission.
Okay, now we have another picture here. It looks like
this shows the 2 spacecraft that went to the moon together. So the top gray spacecraft is the Lunar Reconnaissance Orbiter, which sat on top of the LCROSS mission. The bronze cylinder below it is the LCROSS shepherding spacecraft. The 2 project managers, Dan Andrews, the LCROSS project manager, and Craig Tooley, the LRO project manager, are the fellows there in the garb. And we were what was called a secondary payload. LRO was the primary mission. It's in orbit around the moon, making incredible measurements now. We were just a secondary part of that. What you see here in this image is the Atlas rocket that lifted both vehicles to the moon. And the upper segment is called the Centaur. It is what we actually took advantage of. Otherwise, that's ditched in the ocean. We held on to it, and that's what we turned into our impactor.
Okay. And I gather this was a fairly fast and inexpensive mission because you used rockets that were already available. You didn't have to invent everything from scratch.
It had to be that way. It was an opportunistic mission. LRO moved up to a larger launch vehicle and had some extra capacity to the moon. So NASA put out a call saying, what could you do with this? 19 proposals went in, and LCROSS was selected. The rub of it was you had to do it in 2.5 years and for a very small amount of money in relative terms. And so LCROSS had to rely on existing hardware, existing technologies to put it together. One engineer put it very precisely that nothing could be developed just glued. We just basically glued together as quick as we could a spacecraft, a payload, and got it off.
Sounds efficient. Sounds like that's probably the best way to do it. You know, we have another video, our third and final video. This is about the Mars rover. Actually, there are 2 rovers, identical twins, I believe, on opposite sides of the planet. We're going to see a video about that and then come back, discuss that, and also some other topics with space. So let's go ahead and roll that tape.